A very good afternoon to one and all. I am Dr. P M Patil, Assistant Professor in Pharmaceutical Chemistry Department from Modern College of Pharmacy, Nigri. And today, with the continuation of chromatographic separations, we will continue the fourth topic of this same topic. Now, what we designed the selectivity of these factors, which is depend on the separations. How we are decided you have to need to find out the selectivity factors, which is very good thing to find out. Without this, there is a very less information to exactly track what type of solute you separated and what is the qualifications of that, quantifications of that. It's very dependent to find out the selectivity factor. Whether it is needed, because we are needed here to the relatively retention time in the mobile phase to find out relatively retention type of analytes in the stationary phase and in the mobile phase. So we need a selectivity factor for the solute. This is related to the specifically solute. Now, when in last lectures we have already find out a distribution constant, that is a K. Now the distribution constant you see on the screen, that is a sigma Kb upon Ka. So A and B, these are the different type of component present in your mixtures, and you have to find out a selectivity factors which is separated for the A and for the B. So in this, for these selectivity factors, a sigma is equal to Kb upon Ka. So Kb is the distribution constant for the B type of the solute and distribution constant for the A type. Now in this is also defined in a different way. The sigma is equal to Tr, that is retention of the solute and retention of the solute in the mobile phase. Retention of the solute for the A compound, retention of the solute for the B compound minus the retention time of the mobile phase. Okay, so in this formula you also find out the selectivity factors, which is very important for the identification of solute. Now also we have seen whatever the shape of your peak is symmetrically normal or having a error peak. So error is definitely, if the error comes in the normal peak, we call it as a Gaussian peaks. The Gaussian peaks, if you find out in your samples separations, so there are the lot of assumptions you feel is a consideration in order to continuously equation ki what type of samples you are completed, the retention time in the mobile phase, retention time in the stationary phase, and the length of the column, then what type of the distribution constant is needed and what it is find out. So concentration of the solute in the stationary phase, you are right, or the concentration of the solute in the mobile phase. So these all are factors you have to just come to your mind, and you have to parallelize this factor with your peak finding. So in this way, there are the certain observation on the peak, that is a telling factor, and the fronting factor, which is a necessary. So we will see what is a telling factor. So Gaussian peaks is the peaks which is called as a very good way, having a very good height, and a broadness is a lace. So if the broadness is a lace is not spreading, so the peak is definitely high, and you can easily centralize your peak identification. So telling means what? The tell goes in the some long way. You did this way. And the fronting is in the same way. The fronting is get somehow extended to the front side, and telling is extended to the next one side. So this is maybe happening in the telling or fronting factor. So there are the lot of parameters. You identify the telling factors with a certain calculations way, and the fronting factors also you can identify as well as you find out and calculate by the certain good formulas. So this Gaussian's peaks is the normal error peaks. These are we considered a certain when you are doing a lot of trials, and in these trial conditions you feel that generalize when you are taking a trial. So the 10 trial, 12 trials, 13 trials, you feel that there is a certain telling, fronting factor, capacity factors, or there are a lot of parameters comes in between and which is not having exactly their normal values, which is maybe a having these parameters having their standards value. So this is not a matching with your data. So you have to do a lot of parameters with the different type of trials, and at the end of the trials you just go to the statistically equation to just check out your curve. The peak curve is established for a use of derivation for the chromatographic factors. So in this way, the solute move inside the column, their concentration of the zone spread more and more. Then the peak is get broad, the width is a high. So the residency time of the solute is somehow get confusing because the center of the peak is designed to get confusing. So in this way, you have to find out. Now what is the theory of plate theory? What is a plate? The plate is a stationary phase, and in that stationary phase there are the severe slant, just type of the slices. There are a lot of small size of the plates designed in the stationary phase, and they are the solute in the chromatographic separations are just generated between percolated in between the stationary phase and the mobile phase. A multiple partial partitions takes place while the solute gets moving. If you are considering this type of the column we see in the last time of the lecture. So in this column when you are initiated from to move the mobile phase to here and till the end of the year. So this is the length of the column, and the number of partitions of the solute thus experiences inside the column. They are performing the multiple extractions. So the column is like this, and the moving of your solute and the mobile phase through this column, which is having already stationary phase. So this is the individual extractions gate. So individually 1 by 1 millimeter, there were different type of experiences when the solute mobile phase get interacted with the stationary phase. There is certain adsorption, there is certain partitions. So this type of the phenomena happens. So we call it as performing certain multiple extractions, and these are important to find out the each plate represent a single extraction. So in this column there are the huge number of plates available which is having a design in such a way, this type of, if you are feeling this, these are the column. Okay, so each plate is represent a single extraction or partitions processes. So these are the chromatography divided into the different type of theoretical plate. This plate we called as a number of theoretical plate. Okay, so number of theoretical plate is very efficiently playing a role in the separation of your solute. In the separation chromatographic technique, the high number of theoretical plates, the very good separation you feel. If the separation will be increased as the height of the separation of theoretical plate is decreased. It means the number of theoretical plate is, we need a more number, but the height of theoretical plate we should not be we need a very small height, not a big height. If the high height, so the less separations. If the high number of the theoretical plates, is a great separation, but low number of the theoretical plate, the less separation. So in this way, now the second find out the column efficiency and the plate theory. What is the column efficiency? Column has a certain efficiency. Yeah, definitely. The column itself consisting of theoretical plate, which is already fixes in the starting to the end of the column length, and in this column length there are fixing of number of theoretical plate. The number of theoretical plate is fixed 2000, 3000, 4000, 5000 in a maybe 15 centimeter of the column, 10 centimeter of the column, like this of the column is available in the market. So this type of column having this type number of the theoretical plates. The more theoretical plates number is good to show the good efficiency of column efficiency. The efficiency is depend on number of theoretical plate. So how you define this theoretical plate? On the basis of number of theoretical plate available, length of column and height of the theoretical plate. So if the height of the theoretical plate is h, length is the L, and n is, you say that the efficiency of column. The length is increased but this h is always less. So the result of this, the dominator and the nominator is defined. If this is the less, the value will be increased by the L. So if this is the increase, the efficiency of column will automatically increase. So in this way, the column efficiency and the theoretical plate theory is definitely depend on number of theoretical plates fixed in the column chromatography. High number of theoretical plate is very good for the efficiency of column as well as plate theory. So in this way, the plate theory is successfully accounted with the Gaussian shape of the chromatographic peak, but unfortunately fail to account for the zone broadening. If the zone broadening is a high, so unrealistic it is a forming some unamplified fully equilibrium in the each plate. So this is not actually get satisfactory results. Equilibrium is definitely the chromatographic separation is just a dynamic equilibrium as a mobile phase is continuously moving. So your mobile phase should be a continuously moving with the number of theoretical plate, and if the experiments you are repeatedly certain time, certain repetitions, so it may be a chances the peak shape, your peak error get easily dissolved, and there may be a chances to get improvement of your process for the successful separation in the chromatography. So in this way, this is the chances to get equilibrium separation in the carried out area. So what is the definition of the plate height? Plate height is always less. Okay. So when we are selecting the Gaussian curve is related to the variant number of this sigma. What is this formula we are designing? This is a Gaussian curve is related to the number of variants. Now the number of variants means the selectivity factor, distribution of factor, concentration of solute, concentration solute in the stationary phase, concentration solute in the mobile phase, then the width of your peak, then the time, retention time is dependent on the solute. So the velocity of the mobile phase, then velocity of the solute in the mobile phase, in the stationary phase, and length of the column. These are the variable dependency factors, and this if you are defining the plate height. Now you don't know anything about the column chromatography and you just started with your experiments and you don't know how the column we are using. You just know the length of the column and you don't know the plate number and you don't know the plate height. So you know to find out the path which is based on the calculations. So there are different variations you used, and on the different variations you just know the length of the column chromatography. This you have to put it in the different way as a concentration of the solute at the end of the column, then the solute elutions. This is maybe represented in the graphic way. Now in this way the injection is here, the detector is here, is the peak where is the length of the column minus the sigma, that is a Gaussian curve is a represented, and here is the plus, the length is adding the plus, the peak we have to finalize the analyte peak which is presented at the end of the column. So detector is detecting this way, but the peak is having a Gaussian curve area with a